All right, let's get started for today. Welcome to our 7th lecture, actually 6th lecture. So your project 1 is due tomorrow at 5 p.m. One thing to keep in mind is that even if you work in a group of 2, both of you have to submit. We know it'll be the same code, but your grade will not register just based on your partner submitting. You also have to submit yourself into edX to make sure your grade registers. Your homework 2 is out. It's due on Monday. Homework 2 is on constraint satisfaction problems. Any questions about logistics? Yes? The autograder you have is the way you will be graded, meaning that we run that autograder and it generates a score for you, and it's run exactly the same way as what you have. Now, there are some extra checks we run in the background to make sure you didn't do something weird, but barring you did anything really weird, like let's say hard coding a sequence of actions as what you return and so forth, that autograder is the final say in terms of your grade. So, for example, it is possible you have an inconsistent heuristic, but the autograder didn't find those pairs of states where it was inconsistent and gives you full grade nevertheless, and you'll have a full grade. If you find such things, let us know so we can improve the autograder and next year it won't be true anymore. Any other questions about logistics? All right, so today we're going to start looking at adversarial search. Let's look at some kind of popular examples first. So this is really the kind of standard inclination of adversarial search is game playing. One of the first things people did once they had computers was try to build programs that can play games. And so back in the 50s, a popular game was checkers. And in 1950, the first computer program was written to play checkers. By 1994, the best computer program for playing checkers beat the human world champion, who had been the world champion for 40 years. Okay? So, at that point, there was a computer world champion. Then by 2007, checkers was solved. Now, we haven't formalized what games are, so you don't yet know exactly what it means to be solved, but essentially what it means to be solved is that the computer knows exactly how to play optimally, meaning that if there's a way for the computer to guarantee a win, the computer will guarantee itself a win. It also means that the computer can tell ahead of time. If I'm playing against the perfect human player that just knows everything, computer can tell whether white will win or black will win or whether it will be a draw for this type of game. Okay, so checkers solved. Another game that got a lot of attention after that was chess. In '97, Deep Blue, which is built by IBM, defeats the human champion Garry Kasparov in a 6-game match. Okay? Deep Blue did so by examining 200 million positions per second. It was a very sophisticated evaluation function, which we'll talk about later, and some undisclosed methods that only the people working on it know. Some lines of search, Deep Blue was expanding up to 40 ply, meaning it was thinking 40 moves into the game ahead from where the game currently is to decide on what move it's going to make. Since then, computer programs have gotten even better at playing chess, but maybe there's less attention to it because the human champion has already been beaten. So it's not solved though, in that it's not known who can guarantee themselves a win or whether it's a tie if you have only optimal play. Go, another board game. For Go, it turns out computer players are getting pretty good, but human players are still better. One of the big differences between Go and these other games is that Go has a very large branching factor. And so you can imagine as a computer is trying to explore all possible outcomes from a certain board situation, when the branching factor is high, it's very difficult to do that. And so it might run out of time, might not be able to look at all possible outcomes within the time it has, and so can't play as optimally as, let's say, it could for checkers. One of the main things that's come up there is Monte Carlo evaluations, which means that the computer actually plays out some of the possibilities at random and just sees kind of on average, if I play out at random from this situation, how often does this situation lead to a win for one player versus a win for the other player. Okay, so that's expert level, but not human world champion level. Pacman. Nobody's really tried, but I guess we build AIs for Pacman in this class. About 100 other classes, I believe, that also use these projects. But it's not clear whether the computer is better than the best human players or not. So let's leave that open. Let's look at the first demo. So this is what will be the outcome of your project 2, or it could be the outcome if you do well. This is Mystery Pacman. And so what you'll see here is the result of running adversarial search to drive the decisions that Pacman is making. All right, so this case, Pacman wins. Once we're done with this lecture, you should be able to build the same kind of AI as you see in action there. So let's take a look at how we can formalize all of this. So the main topic will be adversarial games. But before we fully get into that, let's just look at what types of games are there. There are different axes along which we can classify types of games. A first axis is the fact whether the game is deterministic or stochastic. So the games we've talked about so far, Go, checkers, chess, are deterministic games. But there are other games that are non-deterministic, such as backgammon, where there's a roll of dice before you make your move. Poker, where it's stochastic which cards from the deck you get served and which ones unfold on the table. There could be 1, 2, or more players. 1 is kind of a degenerate case. It will degenerate to what we've already covered in the first few lectures. 2 is the adversarial case, but there could be more than 2, even in an adversarial setting. The game could be zero-sum or not. What that means is there's something, some quantity. If it's zero-sum, there's some quantity you care about. Let's say win, lose, or draw are the possible outcomes. You could say the utility of an agent is 1 when they win, -1 when they lose, and 0 when they draw. Now, if you have 2 agents play each other, when the game is over, the sum of their utilities will always be 0. But it could still be 1 for one player, -1 for the other way around, or 0, 0, and so forth. But the zero-sum game is one where the utilities always at the end of the game are such that the 2 players' utilities sum to 0. So they're opposite of each other. Then there's perfect and imperfect information games. Poker is an example of an imperfect information game because you don't know what the cards are that the other players are holding during the game until maybe it's too late. So what we want is, once the game has been formalized, to find a strategy, which we'll also call a policy, which says, for any given situation that we encounter, what is the right move to make in this game? So here's how we could formalize deterministic games, and these are the ones we'll be looking at in this lecture. Next lecture, we'll look at non-deterministic games. So states, there's a set of states, just like in search problems. These are the possible configurations of the world or the part of the world that's relevant to what you're doing. There's some start state. There are a set of players from 1 through n. Usually they take turns. It doesn't have to be that way. There's a set of actions for each player in any given state. There's a transition function. This is what we used to call a successor function, and it's saying for each state and each action what the next state is going to be. Then there's a terminal test. This is probably reminding you of a goal test. It's checking, is the game over or not? And then there are terminal utilities, and this is something new here. So what happens in these games is that when the game is over, a score is associated with the outcome of the game. Each player will have some utility at the very end. And those terminal utilities are what every player wants to optimize. So solution for a player is a policy that says for each state what action to take. So zero sum means that the agents have opposite utilities. So if it's a zero sum game, and the games we'll look at today in this lecture will be zero sum games, then you don't have to consider both players' utility values, because player A's utility value will be the negative of player B's utility value. So we can just keep track of one number rather than keep track of a number for each player. And that's what we'll be doing. But keep in mind that in general, there's a number per player. It just happens to be the case that in zero-sum games, they're opposite, and so one number encodes all the information. So this results in pure competition because an outcome that's good for one player is bad for the other player, and the better it is for one player, the worse it is for another player. Now, general games don't need to have these zero-sum utilities. Agents could have completely independent utilities, and they could act pretty much independently. There could be all kinds of structure to the utilities at the end of the game, and depending on the utility values, these strategies that emerge for each of the players could be strategies where they cooperate, could be where they're completely indifferent to each other, could be that they compete, and it could also be a mix of those, depending on how initially the game starts out. Maybe these two agents start competing and these two start collaborating and so forth. So we'll see more of that in next lecture. So today we'll focus on this type of games, zero-sum games. So this is adversarial search. Let's first look at how we could formalize this kind of search when there's just one agent, because we already know that scenario, and from there we'll generalize to the multi-agent case. So when we run search for one agent, we have a search tree. It has a start state at the top. Then from there we can see what the transition function tells us in terms of next possible states. In this case, Pacman could move left or right. Then from there again, it branches based on the actions available and so forth. This keeps going. Okay, what's new here is that we're going to put utility values at the leaf nodes of the search tree. So for example, this is a leaf node and it has a utility value of 8. Then all of these, if you go far enough down at the very bottom, will reach terminal states. And once they reach a terminal state, there will be utility values associated with those terminal states. Okay? We've seen utility values at the leaf nodes. We'll propagate those up, and that will be something called the value of a state. So for terminal states, the utilities are the values. For non-terminal states, the value of that state is the best achievable outcome from that state. So very easy for terminal states, you already know it. For a non-terminal state, for example over here, if you have two actions available, the value of that state will be the utility you achieve when you take the best of those two actions. So here you have an utility of 8. Down here, the highest is 6. So there you take the max of those children. In this case, that would be 8. And the value of this particular node here would be 8. Okay? So values can be computed just starting from the bottom of the tree, propagating things up, maxing at every node in the tree. Now let's take a look at adversarial game trees. So in this case, Pacman is one player, the ghost is another player, and they'll play against each other. Pacman has a utility that relates to the score of the game. It is actually the score of the game what we do here. The ghost utility is the negative of the score of the game, so this is a zero-sum game. And when we show numbers on the slides, we'll just show Pacman's utility, but keep in mind that the ghost utility is the negative of that. And the ghost is effectively minimizing the score we're showing on the slides, which is Pacman's utility. Okay, so first action is for Pacman. Could be left or right. That's the result. Then it's the ghost's turn. Ghost can move left or right in both of these cases. So we'll have a branching on that. And then this keeps going. And then at the bottom, there will be values there corresponding to the score of the game at the terminal states that you reach. Okay, so that's the definition of the game. Now, Minimax values are values we associate with each of the nodes in this search tree. Okay? So at the terminal states, the Minimax values are just the utilities. We're considering the utilities of Pacman, so these are the Minimax values over here. Let's assume this was a game that only allows for one move by Pacman, one move by the ghost, and then the game is always over. So we have terminal states shown there in this new type of game that allows only for one move each. Then we can propagate these up. So for example, if you're curious about what is the Minimax value of this node over here, the ghost gets to play. Naturally, the ghost would pick the action that minimizes this score, so the ghost would pick this move, and accordingly the Minimax value over here would be -10. Okay. In general, whenever it's under the opponent's control, at that type of node, you take the min of the children, and if you're at your own node, as a maximizer, you take the max of your children. So you can propagate this up. There's a -10 over here, -8, -5. The ghost will choose the minimal value, which is -8. And then over here, the maximizer node will pick the maximum of those values, which is -8. So the Minimax value of this top state over here is -8 for this particular game. You can do this for any game, any adversarial game. You can draw out the entire search tree if you have the time to do it. And you can compute the values of each node in that game tree. So here's another example of a game, Tic-Tac-Toe. So there's a 3x3 board. First, the X player gets to make a move. There are 9 options. Then the O player gets to make a move, has 8 options from each situation after the first move, and so forth. The game is over when all the squares have been filled. You reach a terminal state. The values of the terminal states could be 1 if the maximizer, which is the cross player, wins, -1 if the minimizer, which is the O player, wins, and 0 if it's a tie. Okay, so now we actually can define what it means to have a game be solved. Initially I said checkers is a solved game. Let me now clarify what that means. Let's say you draw out the entire search tree for a game, in this case Tic-Tac-Toe. You could compute the Minimax value for every node in that tree, and then you'd obtain some value at the top over here. This value could either be, in this case, -1, +1, or 0. It will be one of those 3, not a combination, just one. Not an average of them. There will be just one value, -1, +1, or 0. In fact, for Tic-Tac-Toe, I'm pretty sure it'll be 0. If you both play optimally, it'll be a draw. So we propagate all these values up from the top. We find the 0 here. Now we have solved the game of Tic-Tac-Toe by doing this. We have shown that if both players play optimally, it's guaranteed to be a draw. The value of the game is 0. Okay, so let's take a look at adversarial search algorithms. So we're looking at deterministic zero-sum games. Tic-Tac-Toe, chess, and checkers are examples. One player maximizes the result, the other one minimizes it. There will be a search tree, such as the one shown on the right. The players will alternate turns, and what the Minimax search will do is compute each node's Minimax value. So what does Minimax look like? The Minimax search algorithm applied to this game over here? Well, it would first, let's do left to right traversal. So first would look over here, that's 8, this is 2, this is a minimizer, so it would be 2. Then we'd look over on the other side, 5 and 6, it's a minimizer, so that would be 5. And then the maximizer picks the maximum of its children, that's 5, and we've solved the game. Then also you can pick actions based on that. The way it'll play out is the maximizer would pick this action because it leads to 5. Minimizer will pick this action because it leads to 5, which is the best option available to the minimizer. And that's how the game will play out if both players play optimally. Okay. How do we implement this into code? Right? So, because what I've shown so far is just we look at something on a slide and we propagate values up. But in code, we want to run a search algorithm. We don't want to lay out the entire game tree before we start doing anything. The game tree might be really large. So the way it'll play out is effectively a depth-first search. And there'll be 2 types of calls in a depth-first search. There will be a max value call and a min value call. Max value for a state, when it's called on a particular state, initialize its value to -infinity. That's the worst case when you're a maximizer. It can be worse than -infinity because you want the highest possible value. And then it investigates each successor state, computes the value of that successor state, checks if it's better than the current running best value v. If it's better, it'll overwrite what you had. Otherwise, you'll just retain what you had. Loop through this. Once you're done with this loop, you have inside v the highest value among all your successors. You return that. Now note here that there is sometimes a recursive call to another function, min value, which looks exactly the same, but now finds the minimum value of its successors, initializes at +infinity, and then sees if it can find anything lower than that among its children. So this goes back and forth between these two, each of them computing respectively the max of their successors and the min of their successors. Often, when you implement it, it's easier to implement it slightly differently. So you'd have a dispatch function, which computes the value. So you start with a call to, let's compute the value of the current state. Then you look up in the definition of your game for the current state, who gets to make a move. If it's a terminal state, the game is over. You just return the terminal utility. If the next agent to get to make a move is the maximizer agent, you return what you get from the call of max value for that state. If the next move is to be made by the minimizer agent, you call min value and return its return value. So you get this dispatch, and next lecture we'll also see that there are other options that can pop up once you have non-deterministic games. But for deterministic games, zero-sum games, this is what it would look like. Any questions about the Minimax algorithm? All right. So let's look at an example. So here is a Minimax or a adversarial game, zero-sum, that we'll solve with Minimax. We're going to look at it from the perspective of the computer running the search. When the computer starts, there's just one thing available. Really, it's the current state, the start state of the game. The computer will loop through successors of that start state, first visiting the first successor over here. We'll realize it's not a terminal state. It will then, for this one, loop through its successors. It will see that the first one is a terminal state. It has a value of 3 at this point. So we have here at the top a value of -infinity so far. This one here is a value of +infinity. It gets back to 3. So the +infinity gets overwritten by 3 because that's lower. Then it gets the value of its next child. That's 12. That's higher. That's not as good for a minimizer, so the value stays 3. Then there is 8. Again, not as good for the minimizer as 3, so it stays 3. It passes back up to 3. This one here updates its value from -infinity to 3. Then starts looking at the next child. Next child, its value gets initialized at +infinity because it's a minimizer. Looks at its children. 2 is better for the minimizer, so this gets overridden. Then next child 4 stays 2 as a value. Next child 6 still is 2. It's done with looking at all its children, passes the 2 back up. 2 is worse for the maximizer, so the 3 stays. Moving on to the next child. Initially here, in this loop, the value is plus infinity. Looks at its first child, 14. That's better for the minimizer. Next child, 5. That's even better. So this gets overwritten. And then 2 is even better, gets overwritten. Then the 2 gets passed back up. 2 is worse for the maximizer, so it stays with 3. And now we know that the value of the game is 3. And the game will play out if both players play optimally. First, the maximizer will move left, and then the minimizer will move left, and we'll end up with this outcome over here in the game. Okay, what's the efficiency of this search algorithm? This can be run as a depth-first search, where you traverse depth-first, left to right, through your search tree. We know what the complexity is of depth-first search. Time complexity, b to the m, so it's exponential in the depth of your game. The longer your game is, the more moves it has, the more difficult it will be to run this in a reasonable amount of time. Space complexity is b times m. Again, just because this is depth-first search, and that's the amount of information it needs to keep in memory while it's running its search. So let's look at an example. Chess. Branching factor is approximately 35 on average. The length of a game is approximately 100 moves. Again, on average, because in principle it could take longer, but these are just average values. So b to the m is a number that's far too high to run this. Okay? So question we'll ask ourselves is, do we really need to explore this entire tree? Because if we need to, it's going to take too long. We'll need to find approximations to what I just described to be able to come up with a decision in a reasonable amount of time. Okay, so let's look at some properties of Minimax and then start looking at how we can make some approximations. So here is a Minimax game tree. If we play the Minimax strategy, what would happen? Let's compute the values. So we're playing on the left here, 10 is the value. On the right here, 9 is the value. So the value of the game would be 10. And the game would play out this way, or this way. All right, so that's optimal if you play against the perfect game-playing machine. But at the same time you look at this, you might be tempted, and you might say, well, I see a 100 down here. A 9 is not that much worse than a 10. Maybe you feel like you should take your chances and take that other move, because the 9 is just a little bit worse. And what if the other player maybe looks like this? Maybe they will make that wrong move, and you could get out a utility of 100 instead of a utility of 10, and so playing the other way would actually be better. Let's take a look at this in action in a Pacman scenario. So let's first look at the case where we play against mastermind ghosts and see what happens. So Pacman's playing against really good ghosts. Pretty grim scenario. Let's see what happens when we play. All right, let's look at this again. But let's think through what's happening here. So what's happening? What are the utilities in this game? Your score goes up by 1 when you eat a pellet. Actually, your score goes up by 10 if you eat a pellet. Your score goes down by 1 any time step that passes, so the longer things take, your score ticks down. If you win the game, you get a bonus of 500. So sometimes the best possible scenario here is that Pacman would somehow manage to eat all these pellets, which would be a score of 4 times 10 is 40. Winning the game, 540. And then losing a few points because it takes time to eat all the pellets, so maybe -8, so it'd be something like 532 would be the best possible outcome if you look at that game tree. Now, of course, the Minimax value is not 532 because the ghosts play against Pacman, and actually the Minimax value of this is much worse than 532. What's happening here, you look at the Minimax tree. Well, if Pacman were to move to the left, it'll take 2 steps before it dies, and so it'll be penalized twice. If it moves to the right, it only loses 1 point before it dies, so it gets less of a loss, and so it decides that suiciding is the optimal strategy in this kind of world, as we saw in action. So this is actually the rational thing to do here. It's the right decision for Pacman in this particular game. Now, the real world might not be as grim as Pacman's world was envisioned. And you can imagine that, well, maybe the blue ghost is going the other way. What if the blue ghost is not super smart and is playing suboptimally? It's not playing the Minimax strategy. It's just randomly picking whether it should move left or right, up or down when it starts. Now, if it happens to move away from Pacman, that's your lucky case. You could go chase behind the blue ghost, eat all the pellets, and be victorious. Now, if it happens to roll its dice the other way and comes to Pacman, it's a bad outcome still. But in this scenario, and we'll see how to compute this kind of cases next lecture, but just to give you the idea, what will happen is Pacman will decide to run the other way. This case, it was unlucky, and it actually was even worse than suiciding the outcome. But on average, if the blue ghost is a dumb ghost and arbitrarily picks which way to go, on average, it's a good decision to go left. Of course, on average doesn't mean it happens half of the time when you only run it 2 times. So let's see if we can get a lucky outcome here. Oh. Not good. Let's try another time. Oh. The coin is flipped the wrong way every time here so far. Let's give up, but let's keep in mind that if the coin came out the right way, the ghost would have moved the other way, and it would have been a good decision. And the loss by going the wrong way is pretty minimal, so even if only 1 out of 100 times the ghost moves away, it's the right move to go left if it's a dumb ghost. That's not Minimax. The reason I want to highlight this here is that while we're studying Minimax, it's good to be aware of the assumptions we're making. Minimax is an algorithm. It doesn't mean it's the right algorithm for every situation. It is the right algorithm if, or the right strategy if everybody's playing optimally. Okay, so the big problem with Minimax, of course, is that if your game has more than just a handful of moves in it, it becomes impractical to search all the way till the terminal nodes, and you won't be able to find the value of your game. So when we have resource limits, we need to do something else. We won't be able to search through the leaves. We can do something called depth-limited search. What is depth-limited search? Instead of searching all the way to the bottom, only search to a fixed limited depth in the tree. So you pick some depth that you say, well, that's how deep I'm going to go, no deeper than that. Of course, when you hit those nodes that are not at the bottom, there will be no terminal utility values. So you won't know what the utility is of those nodes. You don't have a number to pass up. Well, you don't have a correct number to pass up, but you can define some evaluation function, which you'll have to come up with yourself. It's not part of the definition of the game, but you can somehow try to evaluate some approximation of what the value is of each of those nodes where you stop going down in the tree, put some numbers there, and work with those, and hope that those numbers were good enough approximations of the real numbers for those nodes. And if they're good approximations, this works well. If they're bad approximations, this will not compute something great. Okay, so let's say you have about 100 seconds to compute. You can explore about 10,000 nodes We can check about 1,000,000 nodes per move. If you also run alpha beta, which we'll see at the very end of this lecture, which kind of avoids some parts of the tree in a clever way, you can search up to depth 8. And so you'd have an evaluation function that's being called 8 moves away from where you currently are in your game. Okay, no guarantees of optimal play anymore once you do this. The deeper you search, the better your results will be, the more accurate they will be. So it makes a big difference to implement your search to run as fast as possible so you can go as deep as possible. You can run iterative deepening, something we looked at in the second lecture to get the best of both worlds between breadth first and depth first. You can use that here too. So you might not know how long it takes to search up to depth 8. You might not know how long it takes to search up to depth 7 and so forth. So what you could do is you could say, first I'm running search up to depth 2. It returns a value based on search up depth 2. If anybody makes me decide at that time what move to take, I can use the value I found so far from depth 2. Then you run your search again up to depth 3. You now have a new value, accordingly maybe a new move. If you're called upon making your move, you can use that move. If you still have time left before you have to make your move, you can now search up to depth 4. Keep repeating this until you run out of time, at which time you return the value of your last depth search that you completed. Okay? So this allows you to have an anytime algorithm, and this anytime here refers to the fact that as you are allowed more computation time, you will keep computing and you will improve your answer, but from the very, very beginning, you will already have an answer. Okay, so depth matters because evaluation functions are always imperfect. The deeper inside your tree you go, the less it matters that your evaluation function is not as accurate, and the better your outcome still will be, even with an evaluation function that's not as good. And so there will be a trade-off here between, do you spend computational cycles on a really good evaluation function, but then you won't be able to go as deep? Or do you spend your computational cycles on going really, really deep in a tree and use a very cheap evaluation function, but that's not as accurate maybe? So let's take a look at what happens when we run depth limited search in some Pacman scenarios. So first we'll look at a depth 2 search. So we're only looking too deep. This is the scenario. Okay. Let's see what behavior emerges from a depth 2 minimax with an evaluation function that measures, that scores based on how close Pacman is to this dot and how far Pacman is away from ghosts. So further away from ghosts is good, closer to the dot is good. Okay, let's see what happens. Pacman moves first. Ghost going. All right, so that was the first outcome. That was depth 2 search. Now let's take a look at what happens with a deeper search. We'll search up to 10 moves into the game for Pacman. Keep in mind that ghosts can only change directions when they hit a junction. So once they commit themselves to a direction, they keep going until they hit a junction. So now we're looking 10 deep. Let's see what happens. Pacman first moves up. It gives it time to see what the blue ghost is committing to. It can go the other way and actually win this game. Okay, so this is a good example of why looking further ahead can give you a big benefit. Let's now take a look at what evaluation functions we can put down in these non-leaf nodes. Let's look at the game of chess. We know we're not going to search all the way till the end, so we somehow need to, for any given board situation that we encounter, that's at the end of our search where we have to compute a value, somehow have a single number that determines how good a situation it is. Now, what would be the ideal number to return if you had the perfect evaluation function? It would be a -1, a 0, or a +1, depending on who would win the game when playing optimally from that situation. Okay? But we don't know for most situations whether it's -1, 0, or +1, and so we need something else. Now you might say the most direct, straightforward thing to do would be to just kind of guess, is it more likely to be a loss, a draw, or a win, let's say for the maximizer, and accordingly assign a -1, a 0, or a 1. But then for many, many board situations, the values will be roughly the same, or will be exactly the same even, and it won't be a very distinguishing evaluation function. So in practice, what you do is rather than trying to guess a specific outcome, namely -1, 0, or 1, you pick a real number as your evaluation function number and compute it, for example, like this. So you would say, well, what matters to the kind of quality of the board situation? Well, maybe what matters is the difference between the number of white queens and the number of black queens left. Maybe what matters is the difference between the number of rooks left, the number of bishops, pawns, and so forth. You might care about other features. So each of these will be a feature. We have a first feature, difference in queens, second one, difference in bishops, and so forth. After we covered all pieces, you might say, well, does anything else matter? Is it just about the difference in number of pieces? Well, the weighting between them might matter. It might be more important that you have an edge in number of queens than an edge in the number of pawns. So there are weights there, W1, W2, and so forth. There might be other features that matter. Maybe there's something about mobility. How mobile are your pieces on the board? How protected are your pieces, and so forth. For each of those, you could think about the game and come up with a function that says mobility is this good, how well my pieces are protected is this good, and so forth. These would all be features. You could have n of those, and then you combine them in a single number by taking a weighted combination of them. Okay, so in this case, this is what it looks like. Do you have to take a linear weighted combination? You don't have to. You can compute a combination of those features. You could take some nonlinear function of them, maybe the max, maybe it's something else. But it turns out for a lot of algorithms, it's very convenient if you take a weighted combination of features. So that's the example we'll look at for now. So how about Pacman? You'll have to think about this for your projects too. What will be your evaluation function for a board situation? For example, this here. What number are you going to come up with, right? Well, you might think about things like distance to the ghosts, distance to the nearest power pellet might matter because it's better when you're close to one, maybe you're safer, and so forth. So you come up with a bunch of things that you think that matter. Then you assign some weights to them to compute a single value. Then to make sure that you actually pick something reasonable, what you want to do is you want to inspect board situations. And you want to make sure that the evaluation function assigns better numbers to board situations that you think are better and worse values to board situations that you think are worse. So you'd look at a situation and say, well, how is this situation, let's say, compared to this situation? Well, this one is worse. So you'd make sure that your evaluation function indeed is worse for this situation. Worse meaning a lower number. Now, how about this situation? Seems about the same as the previous one, so maybe your evaluation function is the same, or maybe it's even slightly better because you ate one more pellet and so you're a little further along in the game. How about this situation? A lot worse. So you want to make sure that your evaluation indeed gives you a number that's much lower than the numbers you get for any of the other situation. And this one, even worse. And so this is something you want to do at debugging time if your Pacman doesn't behave right. Often it won't be that your Minimax implementation is wrong, because that's just a few lines of code. Often the behavior isn't what you want, because the evaluation function isn't a good evaluation function, and then it just doesn't generate good behavior. All right, let's take a short break here, and after the break, let's take a look at what can go wrong with these evaluation functions. So, first one. Okay, what's going on underneath here? We will run a depth 2 Minimax search. Well, Minimax, there's no maximizing player. There's no minimizing player here. It's only the maximizer Pacman. So essentially looking 2 moves into the future for Pacman. We have an evaluation function that is how many food pellets have been eaten so far from the board. Okay. And anything else about the scenario here? Let's see. That's it. Actually, it's looking three steps ahead in this example here. Okay, here's Pacman in action. First move, seems pretty good. Second move. Third move. Fourth move. All right, so what's happening here? So the evaluation function is just how many food pellets have been eaten so far. Very simple evaluation function. All right. It's looking 3 steps into the future. It's realizing that from this situation, if you only get to look 3 steps into the future, this is clearly the best move. But then from here, if you get to make 3 moves, there's actually a bunch of options that are equally good in terms of how you start out. There's a tie. Going down and eating the food pellet right away is a good option because ultimately after 3 moves, you'll have eaten a food pellet. In fact, you did it in the first move. But if you first move to the left, then you still, in a total of 3 moves, will have eaten a food pellet. So it's equally good according to this depth research. And keeps going like that. And so effectively what's happening here is that it makes this plan that where it thinks 3 steps ahead, and thinking 3 steps ahead, it's a pretty good plan. Then after it makes the first move, it replans. And thanks to that replanning, things kind of unravel, and it kind of just keeps thrashing back and forth and never goes to eat the food pellet. Okay? Replanning is, of course, a good thing. Really what's happening here is that it actually doesn't know how to distinguish between a move that will make it take 3 moves to eat the food pellet versus a move where it would only take 1 move to eat the food pellet. The evaluation function is the same. Now, if we had something in our evaluation function that would favor eating the food pellets earlier, for example, if you had in your evaluation function not only how many food pellets you've eaten, but also how close you are to the next food pellet, then eating that food pellet quickly would be better because from there you can move on to the next one, and once you combine both features in your evaluation function, you'll get a better score for the thing that eats the food pellet right away and then starts moving towards the next one. But for this naive evaluation function, you get this thrashing behavior. It's something you might also see in your projects. As long as your evaluation function is not very good at distinguishing between states, it might think a lot of states are equally good, and you might get this kind of behavior where Pacman kind of goes nowhere. Okay, now let's take a look at this on the slides to kind of spell it out. So Pacman Starving here. If you look at the game tree, in kind of a simple played out scenario, even smaller than the one in the game we watched, it's kind of after 1 move. In one case it ate a food pellet, the other case not. But then after 2 moves here, there are actually 2 equally good outcomes. This one and this one, according to a naive evaluation function, are equally good. And so it could decide that this is the way to play the game. But then remember, it's going to replan. So all that happens is it makes its first move. It's over here. It's a symmetric situation from where it started from. It can go through the same reasoning, break ties the same way, and then move back to where it came from, and you get this crashing behavior just in this very small game tree over here. Okay, so The problem here is that eating later seems just as good as eating earlier. And so, for example, the score here could be 1, 0, 1, so to say. This is 1. This is 1. Score at the top is 1. And so things are equally good at the top. And so that's why we get this thrashing behavior. Now, a small tweak to the evaluation function would fix that. Let's say we also include, we want distance to the next food pallet to be as low as possible. So maybe we include plus 1 over the distance to the nearest by food pallet. Same thing here. Same thing here. Now, on the left here, that would give you an evaluation of 1. This 2 moves away, so it'd be 1 plus 1/2. In the middle here, it would be 0 plus 1. And on the right here, it would be 1 plus 1 over 3. Now if we propagate values up, we get 1 plus 1/2 over here, 1 plus 1 over 3 over here. The 1 plus 1/2 will win, and it'll actually make this move and play the game in a much better way. Look at this in action. Change the evaluation function, looking at the same scenario as we had before. Let's see. We use this better evaluation function. First move still the same, but now second move actually goes hit the pallet and it makes it all the way, both of those pallets in the optimal way. Okay? Okay, here's something else I want to take a look at with you. We're going to look at Minimax from the ghost's perspective now and see what kind of behavior emerges if the ghosts play Minimax. Now, what's interesting here, there are 2 ghosts, right? So we essentially have Pacman makes a move, Ghost 1 makes a move, Ghost 2 makes a move, and Pacman makes a move, and this repeats. So we'll have the ghost playing Minimax. This is our board. All right, what happened here? The ghost kind of, let's zoom in actually on what happens instead of looking at it this way. Let's really zoom in on what happens in this kind of scenario. So here's a zoomed in version of a similar scenario. Okay. Let's show this on the board or on the screen here. So what's happening here? The behavior we saw emerge is that the ghosts actually collaborated. Right? They didn't just chase after Pacman. They went different ways so they could corner Pacman and win, at least from their perspective. Now what's interesting here is that this actually is just Minimax, and that if you were to write the AI for these ghosts, you can run Minimax for Ghost 1, Minimax for Ghost 2. Each of them could independently run Minimax as independent players. And they will still coordinate this way. Why? Because their utilities are the same. They both ghosts have a utility that's very high when they win the game. When the ghosts are considering possible scenarios, they realize if one ghost goes one way, if then I go the other way, my utility will be very high. And so you get this cooperative behavior, in this case against Pacman, but cooperative among the ghosts, emerge naturally from this game tree where 2 of the players have the same utility. Yes?
Would we still say that both ghosts
Say that again?
If both ghosts are at the same position, would we still see that behavior?
So the question is, what happens if both ghosts start out at the same position, right? It doesn't depend so much on whether they're at the same position. What they need to know is how the game is played. And so in this case, the game is defined as Pacman moves, then one ghost moves, then the other ghost moves, and this repeats. And so they know the order of play. And so they know, in some sense, what the other ghost is going to do, because they know the other one will play optimally, and so forth. And so if they start at the same place, yes, they would need to somehow move apart. After one makes a move, it'll have separated itself from the other one. The other one will realize what now its optimal move is, and they'll still flank to corner Pacman. The key here is that there is a utility function that they share, and that that both ghosts optimize, and so the optimal behavior, even if independently computed, will be cooperation. Okay, so last topic for this lecture is pruning. So let's look again at our Minimax example. So we run Minimax on a game tree. We start at just the start state. We call successor function, see what we have. We loop through the successors. We see that we reach a terminal state. The terminal state value is 3. That will be our current running value here. Next value is 12. That's worse for the minimizer, so we keep 3. 8 is worse. We pass the 3 back up. Our current running value here starts out as negative infinity. The 3 makes that better. It becomes 3. Go look at the next child. Next child loops over its children. Starts out with a value of plus infinity because it's a minimizer, but that becomes 2 because that's better. 4 is not better than 2 for the minimizer. 6 is not better. Keep going. 2 is passed back up. This stays 3 because 3 is better for the maximizer than 2. Then go down here. Initial value is plus infinity for the minimizer. 14 is better, so it becomes 14. Then 5 is better, becomes 5. Then 2 is better, becomes 2. 2 gets passed back up, but 3 is best, and so the value of the game is 3. That's the entire computation we did. We realized that for games with a lot of moves and or a large branching factor, you might not be able to get to the terminal node, so we looked at evaluation functions and to be able to stop at a certain depth. Now we'll look at another way to improve computation to find the value of these game trees. So let's take a look at what we just did and see if we can reduce the amount of computation, but this time without losing accuracy. So what we've seen so far with evaluation functions reduces the accuracy. And it will always be necessary for large games, but there's also a trick we can play that doesn't reduce accuracy and still helps us to speed things up. So this is called pruning, and let's take a look at how this plays out. So we're in this, running this algorithm, chucking along. Now we hit this point over here. Let's look at the status of the algorithm. At this point we had a 3 over here that's been passed up, that's sitting here as the current value. This is now 2. What do we know is going to happen next as we run the algorithm? The standard Minimax algorithm will look at these children over here, look at their values. What's the result of looking at those values? We haven't seen them yet, so we don't know yet what the result is going to be, but we know one property of the result. It'll stay 2, or it'll become smaller. We already know the maximizer has an option here that gives 3. So anything that's 2 or lower will never be picked. So this action here would never be taken by the maximizer. There's no point in investigating what's down here. It will not affect what the maximizer will decide to do. So we can just skip over this. Okay, move on to the next child. Okay, now there's a 14 here. So we have a 14. What do we know about what's going to happen when we investigate the next children? It's going to be less than or equal to 14 after investigating them. Well, 14 is still better than 3, so we can't just skip those children because maybe we'll realize the value is something better than 3, and so we need to know what it is. So we'll look at the next child. Now it's 5. We know ultimately we'll get something that's equal to 5 or lower, but we don't know what it exactly will be. Well, we have an option of 3 here. 5 is still a possibility of being better, so we have to keep looking. Happens to be 2, becomes 2. At this point, it's worse than 3, and if there were more children, we could stop and just pass back up 2 and say it's going to be 2 or worse. You can stop looking down this branch. Okay, so this kind of pruning is called alpha-beta pruning. It's maybe the most complicated idea in this, this lecture, so let's step in through it in kind of great detail here. So we're in some general configuration. We're looking at the min version. So we're right now running our Minimax algorithm, investigating this node over here, n. While we investigate that node, what we do is we loop over its children. As we loop over the children, the value stored here will only go down. It'll start up plus infinity, and then the first child will make it lower, and it'll keep going lower and lower and lower as you see more children. Okay. Why does this value matter? This value would be passed up, and then the maximizer will consider that value as something it might achieve, right? So let's consider the path from this node that we're investigating all the way to the root of the tree. This is important. We're going all the way to the top. Let's look at all the maximizer nodes on that path and look at the values they have so far. One of those maximizer nodes, based on the children it has seen so far, will have the best value for the maximizer. All right, let's assume that's this node over here. Along this entire path to the root, this node, as its current running value for the maximizer there, is the best along the path to the root. And let's say that value is A. So V over here equals A. Okay, now let's consider the scenario where the value we have down here, for the when we're considering values for the minimizer node down there, the value we currently have, maybe let's call it capital V to distinguish it. Let's say our current running value, capital V, is smaller than A. Let's actually make it strictly smaller, easier to think about. Okay, what does that mean? It means this node, after we did full minimax for that node and we find the actual value, we'll find something that's smaller than A, because the capital V can only go down as we look at more children. So ultimately we know we'll find something here that's strictly smaller than A. Well, we know as the game unfolds, when we hit this decision point here for the maximizer can choose to go this way or that way. If going down this path here results in a value of V or smaller, capital V or smaller, that's worse than going down the other path, so the maximizer would never pick it. So we know that if in this branch over here, somewhere for the minimizer, we encounter this value capital V that could only get even lower than A. Once we hit a value lower than A, it doesn't matter how much lower than A it is. If that value bubbles to the top, it's never going to be picked that branch. The game's going to go the other way. And so that's the key idea here, is that once you hit something lower than A, you know that whatever it is, if it happens to make it up there, it's going to be ignored because the maximizer is going to go the other way. And so we can stop exploring exactly what that value is, because how much lower than A it is not going to affect the outcome. That's the version for when we're investigating a minimizer node. So we look at the entire path to the root, look at all maximizer nodes along the path to the root, look at the values of those maximizer nodes, see which one's the best value for the maximizer so far along that path, And we can prune if that best value is better than something we're currently considering for the minimizer. You can do something symmetric for the other way around. And here's what the complete algorithm looks like. So the important invariant to keep in mind is that we have a new variable alpha and a new variable beta. Alpha is the maximizer's best option from where you are currently in your search on the path to the root. And beta is the minimizer's best option on the path to the root, where the path to the root is from where you currently are in your search tree all the way up to the root. So the new max value is a little different from what we had before. Before we still initialize to minus infinity, we still do that now. Then we loop over successors. We still take the max between the value we had so far and what the successor value is. Now, there's a little change over here. We say if the value that we are currently considering, and this is, so actually what we talked about before was this node, so let's look at this one here. We're looking at a minimizer node. We just go back in a value. Our value might have been updated. If the value we currently have as our estimate, running estimate for that minimizer node is smaller or equal to alpha, where alpha is the best option for the maximizer along the path to the root, then we know it doesn't matter how much smaller it's going to be. It's worse, and we can just pass up v itself and be done with it. So we can return right here, which means we actually break out of this for loop and don't consider all successors of that state. Now, not considering successors of the state is actually a bigger deal than just saying, oh, I had 10 things to consider, I'm only considering 2. Remember, every successor has a whole subtree below it, so you're actually cutting out huge subtrees from your search. And this can give you a big speed up in terms of how much you can explore and how deep you can go. Then you need to check if you need to update beta. Remember, beta is the best value for the minimizer along the path to the root. So if you have something better for the minimizer, you have to put it into beta. You go around here. This value of beta is not used in here, except that it's passed into the recursive call for the child node to consider as the best option for the minimizer on its path to the root. Okay, so what are some properties of alpha beta pruning? So interestingly, code-wise, this is actually pretty straightforward, but you can get a lot of gain out of this. And the intuition can sometimes be a little more complicated than the code, and it's true here. So one thing has no effect on the value you get for the root. But what can happen and will happen is that the value at intermediate nodes can be wrong. So if you run alpha beta pruning on this little tree here, you would have 10 over here. You would then go down this path, knowing you already have an option of 10. Now this thing gives you 10. You would then not consider this one, and you'd pass up 10 also from the second side. So both sides are now passing up 10. So just looking at those 10s, you can't even distinguish whether you should move left or right if you're the maximizer node. Now there are some solutions to that, but keep this in mind that the values passed up are not minimax values anymore, but the value at the top will still be a minimax value. So there are a few fixes when you need to pick an action. One fix is to say, instead of running alpha beta pruning from the top, I'm going to run alpha beta pruning from here and from here. So for the children from the top node, now you'll get the correct values for each of the children. You can use those values to decide what action to take, and you can take the optimal action accordingly. Another thing to do, if you think about it carefully, you'll see that this will only, if you have ties, the first time you see the value will actually be the time that you want to keep it, and the second time that you get that same value will be potentially the time that it's not the real value, but that you were pruning. And so if you retain the first branch from which you get that value back, that'll also work. So there's different ways to deal with this. Another way to deal with it would be just say, I only prune on inequalities, not when it's equal. So there's several fixes here, but keep this in mind that just keeping track of the value of the root node is not enough to know which action to take. Okay, with perfect ordering, time complexity drops to order b to the m over 2. What is m? M is the depth of your game. So we're saying here that the effective depth of the game has been halved. This is substantial, right? The exponent is being halved. Equivalently, if you had an evaluation function and you had a finite depth search, maybe before you could go up to depth 8, now you can go up to depth 16 because you're running alpha beta pruning. This is in the best case scenario. Now, you might say, how do we get the best case scenario, right? Because how can you favor getting pruning? Well, one thing to think about here is that it might depend on in which order you traverse your children. When do we prune? We prune whenever there is something better already for the maximizer, right? We get to prune. And correspondingly, we prune whenever there's something on the path of the root that's already better for the minimizer. So the heuristic that a lot of people use here is to say, if you have any idea of which option might be the better option among your children, pick the better option first in your search. Because then you'll put a better number already on that node, and you'll have better numbers on that path to the root, and you'll have a higher chance that you'll get to prune when you're running alpha beta pruning. This entire thing is an example of meta-reasoning. Meta-reasoning means that you are actually thinking about how you are thinking. You're saying, well, alpha beta pruning allows me to not consider parts of the search tree because I know they're not relevant, and ordering things in a certain way to improve your chance of alpha beta pruning is not a way to do meta-reasoning. To say, well, if I think this way, I might get my answer more quickly than if I think a different way. Yes?
The point values of intermediate nodes might be wrong. Does that mean that this isn't friendly to the situation when Pacman is going back and forth, and we took a fraction using the intermediate nodes? So does that mean alpha beta pruning is not like friendly with that situation? That's not a good fix?
Alpha beta pruning is not a fix to kind of completely solve your game. Right? The times it'll work well, meaning it'll always work correctly, but what I mean with working well, it will work well in some sense whenever you prune a lot of branches as you work down your search. And so if you have an evaluation function that has that is not very informative in some sense, you might not be able to prune a whole lot. If you're first exploring all the worst case scenarios in some sense, then on your path to the top, you'll never see that you already had a better option, so you won't prune. But if you explore your best options first and your evaluation function is pretty informative, it'll actually help you a lot in your computation. So let's look at an example here. So if we run alpha beta pruning on this particular game tree, traversing left to right, which branch would be pruned, if any? Any thoughts? Over here. Suggestion was F. Why is F getting pruned? Well, we start left to right. This would be 8. We'd see a 4 here. 4 is worse than the 8 that we already have over there. So we don't have to look at the 50 over here. And we can cut out that branch. How about this one over here? Which branches can be pruned here? This requires some thought, right? So might be a little easier as we annotate the slide. So we start at the bottom here. We'll see a 10. You never get to prune in the very first branch, so we'll see 10 first. Then we'll have to look at the best value. So we'll have a alpha, best for the maximizer of minus infinity, a beta of plus infinity that get passed down. We'll have a alpha of minus infinity, a beta of plus infinity passed down. Same over here. Ooh, it's not taking it. So at this point, first thing we look at is 10. Can't prune because there's no other options available. Maximizer is checking what options does the minimizer have available above. nothing yet, so can't prune yet. We'll look at the next one, that's 6. That's worse, so we keep the 10, we pass up the 10. Now 10 is the best option here for the minimizer. Can the minimizer prune? No, because the maximizer has no better option than 10 yet. The best option of the maximizer is still negative infinity. So we go down the next branch. We go down here, next branch. We get 100. Can we prune here? Can we prune G? Yes. Why? Because the minimizer has a 10 over here. This is 100, which is better for the maximizer. 10 is better for the minimizer. So we don't need to check what's here. Work our way back up. 10 is the best option so far. Work our way down here. Maximizer node, no options for the minimizer above it, so we need to investigate all values. The best is 2. Pass that back up. We now have a 2 here. Best option for the maximizer above it is 10. Here is a 2. Well, maximizer will never allow a 2 to happen, or certainly not anything worse. So we can branch this. We can cross out this branch over here, and we find the value of 10 for the game. All right, that's it for today. Next time we'll look at uncertainty.